Hello, this is Mr. Craig, and I want to discuss one of the review sheets for kinetics, day 106. I won't discuss the math portion in the later parts of this review sheet, but I do want to talk about question number one. Question number one is very unique, and actually I think it appeared on the AP exam as recently as 4 or 5 years ago, and this one really caused a lot of anguish for a lot of students because they came back and they said, "Oh, Mr. Craig, the concentrations weren't the same." And I'm like, "Okay, that's fine. All you have to do is a little bit of algebra." And to be honest, we didn't work any of those types of problems out, and everybody just freaked out. So I want to make sure that you're also comfortable because 2011 is a great opportunity for another kinetics type question just like this, or just like the ones that we've had in the homework. So here's the setup here. We have our reactants, and again, we're not so concerned about our balanced equation. But the data is good data. The designer of this data probably wasn't very brilliant. Whenever you try to do something like this, you try to want to leave the concentrations, have identical concentrations for at least two of the experiments. I mean, maybe this individual was in a hurry for whatever reason. Who knows, who cares? But it's still, you can work this out. Alright, so part A says, determine the order of reaction with respect to each of the reactants listed below. Show all your work. So it's asking you to find the iodine ions first, and that's fine. What's nice is the ClO -1 here actually has the same concentration, so do what we've been doing. Compare those two rates to each other, and again, if you want to go 2 over 1 or 1 over 2, tomato, tomato, it's up to you. You can decide. However, do start with the reactant that has the same concentration. You have to have one of the reactants that have identical concentrations to do this. So doing the work that we're accustomed to, we find out that the ratio is 3.05. Cancel out any like terms. I did not show the cancellation of the constants here, but they are the same. So we're left with just the 0.052 to some power divided by 0.017 to some power. Divide those two values out. Now we have a ratio 3.05 is equal to 3.05 to the m power. Again, your only powers or orders for the reactants can be 0, 1, or 2. What I don't want you doing is freezing up and locking up and saying, "Whoa, that number doesn't look right," or "Oh, try it." If it doesn't work with 0, 1, or 2, then go back and look at your calculations. So we know that the iodine is a first order reactant. All right, knowing that the iodine ions are the first order reactant, now we want to pick two different experiments. And since we don't have alike concentrations for the iodine, pick either 3 and 1 or 3 and 2. It does not matter. You just can't do experiment 2 and 1 or 1 and 2. So it looked like I picked experiment 3 and 1, and again, doesn't matter. Take those rates, take it, divide by each other. In this case, I got 3.82. Nothing really extraordinary about that. However, when I plug in my concentrations, you'll notice that I do have my order included here. The order is the power. So anything to the first power is itself. So we'll take this value divided by that value. And in this case here, I get 0.94. Now, at this point, it's algebra. Whatever that value is, 0.94, we want to get it to the other side of the equal sign. We want to have it with the ratio. So I want to take the 0.94, which is the ratio of 0.016 over 0.017. That's our concentration. Don't round it. Don't make them even. Okay? Don't make a big mistake here. And so once I move the 0.94 over, I have this value, which equals 4.06. That's my ratio of my rates now that I have my orders included there. Now the only thing that I'm left with is a 0.061 to some power over 0.015 to some power, which happens to be the same. Take those values, divide it. Ironically, we get the same number here. So when we go and calculate our power or our order, it's to the first power. So when we finish here, our order is to the first for each of the reactants. And again, you can either write the superscript or you can leave it as a 1. Okay. Once you have that, now the next question is asking you to calculate the value of the specific rate constant K. Pick a trial or an experiment. Doesn't matter which one. It really doesn't. And Plug that value in, and we get around 611 or 610. I'm not sure why I did that. Oh, for sig figs, 2 sig figs. But again, go ahead and write what you're comfortable with. Do include your units. Be unit specific here. So once we have that, again, since we have 2 first order reactants, we're going to have molarity times molarity, and then we have molarity, which is our rate, over time, which is in this case is seconds. So one of the molarities cancels out, and so our units should be 1 over molarity second, or molarity time. All right. This is a continuation of this question, so we're still going on here. It says the catalyzed decomposition of the hydrogen peroxide is represented in the equation below. Again, we don't care about that. Now, it does say it's catalyzed. Now, initially we really don't care if it's catalyzed or not. It just means that the reaction is going a little quicker than normal. All right. The kinetics for the decomposition of this reaction were studied, and the analysis of the results show that it is a first-order reaction. That is huge. Make sure that you know what a first-order reaction is. Well, that's nice because we only have 1 reactant, so the reactant order is 1. Add up all the orders for all the reactants. We only have 1 reactant, so the reactant order is also 1. Okay, so we know that it's a first-order reactant / reaction. You're given some data here. Don't really need it right now. Part C says, during the analysis of the data, the graph below was produced. Now, if we're going to get a negative slope, the question's asking us first to label the vertical axis. So we want to know, what is this axis supposed to be? You know it's a first-order reactant. You have time on the bottom. The only way we're going to generate a negative slope is if we take the natural log of the concentration of our first-order reactant. That's why we have a straight line. Okay. Part 2. What are the units for the rate constant K for the decomposition of hydrogen peroxide? All right. Well, probably not a bad idea to know what your units are for rate. Right there, it's given in minutes. Okay. Or I'm sorry, we don't have the rate there. But do realize that rate is molarity per unit of time. So we know that we have minutes. So the rate law for this reaction is rate equals the constant K times hydrogen peroxide to the first order. All right, so if we know that rate is molarity per minute, and we know hydrogen peroxide is molarity, we're going to move the hydrogen peroxide right below the rate, and we're going to isolate K. So in this instance, the molarities cancel, and we're left with 1 over minutes. Okay. Double I. On the graph below, draw a line that represents a plot of the uncatalyzed first-order decomposition of 1 molar hydrogen peroxide. Now, this question really did give you a lot of information. So we have first-order decomposition for the uncatalyzed. Now, let's recall, what does catalyzed mean? If the reaction has a catalyst, does the rate of the reaction go faster or slower than an uncatalyzed reaction? Hopefully you're saying that the catalyzed goes faster. All right, so what we need to realize with this slope that's given here, this represents the catalyzed reaction. So if it's asking for the uncatalyzed reaction, we're not going to draw any curves, no curves, because the natural log of the concentration versus time, whether it's catalyzed or not, doesn't change. So I don't want to see any curves. We also start at the same point. We are going to start at that point right there. We don't necessarily finish at the same point, okay, in time, but we have to start at the same point. Now, realize that the natural log of the hydrogen peroxide concentration versus time will still yield a straight line or a negative slope. However, do realize that a negative slope that is nearly vertical means that the reaction is very fast. A slope that is nearly horizontal, or a straight line that is nearly horizontal, represents a reaction that is very, very slow. We still want to keep this a negative slope. So if I'm looking at a uncatalyzed representation, I will start at this point right here, at that concentration in time, and then I will do what? How will my slope look? Hopefully you answered that the slope will be above the catalyzed. The reason why is this line right here represents the catalyzed reaction, which is faster. Again, nearly vertical means super fast. Nearly horizontal means super slow. So we want to have some straight line starting at the same point in concentration as the other. And you want to have it above. Now, we're not doing any crazy curves. No curves. Natural log of concentration. I can't tell you how many times I've seen people draw curves on this graph. You have to realize, just because it's catalyzed or uncatalyzed, whether the rate of the reaction is faster or slower, and that's all catalysts do, is speed up or slow down the rate, it's still a negative slope. It's a first order reactant. Alright, I think I beat that horse to death. Alright, looks like we have just math here. So I really wanted to touch on the concepts there, and I really wanted to point out the emphasis. Even though it may not be on the test tomorrow, I just got a feeling that we're going to see something like this on the AP exam. I hope this video's helped. Sorry about dragging that through the mud a little bit longer than I should have.